Hey everyone, Informer here. Today we're diving into the world of Interior Gateway Protocols, or IGPs for short. These are like the traffic directors of your network, making sure data gets where it needs to go quickly and efficiently. Imagine your network as a city. You've got lots of different devices, like computers and servers, all trying to communicate with each other. That's where IGPs come in. They act like a GPS system, figuring out the best route for data packets to travel between these devices. IGPs are essential for any network, big or small. They help ensure smooth communication, keep things running smoothly, and allow your network to grow without hitting any roadblocks. Without IGPs, your network would be like a city with no traffic lights, chaotic and slow. Now, there are a few different types of IGPs, each with its own strengths and weaknesses. Let's take a look. First up, we've got distance vector protocols. These are like old-school map directions. They figure out the best route based on the distance between devices, measured in hops. Think of it like counting the number of intersections on a map. One example of this is RIP, the Routing Information Protocol. It's simple, but can be a bit slow and clunky for larger networks. Next, we've got link state protocols. These are more like modern GPS systems. They keep track of the entire network topology, like a detailed map with all the roads and traffic conditions. This allows them to calculate the absolute best route in real time. OSPF, or Open Shortest Path First, is a popular example of a link state protocol. It's fast, efficient, and perfect for larger, more complex networks. Finally, we have hybrid protocols which, as you might guess, combine the best of both worlds. They offer a good balance of simplicity and efficiency. One example is IGPs, or Enhanced Interior Gateway Routing Protocol, developed by Cisco. It's like a GPS system that also remembers shortcuts and alternative routes. Now let's break down some of the key characteristics and components that make IGPs tick. One crucial component is the routing table. It's like a directory that each device on the network keeps, listing the best known routes to other devices. Think of it like your contact list, but for network locations. Then there's the routing algorithm. This is the brains of the operation, the part that actually figures out the best path for data. Different IGPs use different algorithms, each with its own way of calculating the optimal route. Metrics are another important factor. These are the criteria used to determine the best path. It could be distance, speed, cost, or a combination of factors. Imagine choosing a route based on whether you want the fastest, shortest, or cheapest option. And of course, we can't forget about routing updates. These are messages that get passed around between devices, informing each other about any changes in the network topology. It's like a network gossip chain, keeping everyone in the loop. Like any good tech, IGPs have their pros and cons. On the plus side, IGPs make managing your network a whole lot easier. They automate the process of routing traffic so you don't have to manually configure everything yourself. They also adapt to changes in the network automatically so you can add or remove devices without bringing everything to a grinding halt. But there are a few downsides. Setting up and configuring IGPs can be a bit tricky, especially for larger networks, and because they require constant communication and updates, they can put a bit of a strain on your network resources. Overall, the advantages of IGPs far outweigh the disadvantages. They're essential for any network that wants to keep data flowing smoothly and efficiently. To GAP 3S. In conclusion, Interior Gateway Protocols, or IGPs, are essential for efficient network communication. They act like traffic directors, ensuring data packets find the best routes to their destinations. We've explored different types of IGPs, including distance vector, link state, and hybrid protocols, each with unique strengths. Key components like routing tables, algorithms, metrics, and updates play crucial roles in their functionality. While IGPs simplify network management and adapt to changes, they can be complex to set up and resource-intensive. Overall, their benefits far outweigh the drawbacks. GAP 2S. Thank you. See you in the next one. GAP 2S. But before we wrap up, let's take a closer look at how IGPs are utilized in real-world scenarios. Imagine a large corporation with multiple branch offices across different cities. Each office needs to communicate seamlessly with the others, sharing data, accessing centralized resources, and maintaining connectivity even if one part of the network goes down. Here, IGPs come into play. They ensure that data packets travel the most efficient routes, even rerouting dynamically in case of network changes or failures. Gap 2S. Another example is in the realm of Internet Service Providers, ISPs. ISPs use IGPs to manage the vast networks that deliver internet services to millions of users. These protocols help ISPs maintain optimal performance by constantly updating the best paths for data to travel, balancing the load, and preventing bottlenecks. Gap 2S. In both scenarios, the robust functionality of IGPs ensures reliability, efficiency, and adaptability, making them indispensable in today's interconnected world. Gap 2S. We hope this deeper dive into the real-world applications of IGPs has given you a clearer understanding of their importance. Stay tuned for more insightful content. Thank you for watching, and see you in the next one.